All right. Well, welcome everyone. Uh, Always fantastic to have Bill Shadid with AeroSeal Envelope. If you don't know, Bill has joined the marketing team there and has rebranded from Aero Barrier to AeroSeal Envelope. I know both Gord and I have been very careful in our recent presentations but it's taken some time, right, Gord? We're like that's right, AeroSeal Envelope, and then of course the fantastic AeroSeal product. And then we're joined by Gord Cook with Building Knowledge Canada and Construction Instruction, who's a longtime friend of EVA as well. And I got a chance to see part of this presentation up at the spring camp that you host, Gord, in Ontario. And I think that if you look at what are the most impactful things that you can do for a high performance home with very little embodied carbon cost to it, that this really reveals itself as one of them. So I'm so pleased to have Gord and Bill presenting on the carbon impact of air sealing the building envelope. And gentlemen, welcome. We'll have the Q&A section. Feel free to ask questions there. We are going to hold the questions till the end of today's presentation, and then I'll open those up to our speakers. So welcome, gentlemen.
Thanks, Aaron. Appreciate it. We're both glad to be here. I'll start us off. And as Aaron mentioned, our topic is the carbon impact of air sealing the building. A variety of things we can do in the envelope, like insulation and other things. But we did a pretty interesting and cool analysis of just isolating the impact of air sealing. So we'll talk about a number of other topics around that as well. And I'll go ahead and get us started. As Aaron mentioned, we'll have time at the end for Q&A. And as you can see get my slides to advance. Here we go. Yes, as you can see on our agenda, there's a number of things we're going to talk about, but no worries, we'll get through this at a nice pace that everybody can easily absorb and still leave plenty of time at the end for Q&A. But we'll real quick kind of give you a little bit of background on Gord and myself so you understand kind of who's talking to you and where we come from. Talk about the broader carbon impact of housing in general and why this is a really good and important topic. Talk about the impact specifically of envelope air leakage on carbon. Then we'll cover a little bit of knowledge and insights around both embodied carbon and operational carbon. We also did a separate little analysis that we thought would be a great part of this presentation where we looked at reported air tightness levels by city for 10 different cities in the United States for single family homes, using some data from Ecotrope. And then we'll cover really the meat of this, which is an analysis that we did on air tightness and its impact on operational carbon, and you doing computer modeling. Finish up with how does that relate to carbon impact of a couple other energy efficiency measures, and then quickly review some key learnings and insights, and again have time at the end for Q&A with discussion. So I'll let Gord introduce himself, and then I'll introduce myself.
And thanks, Bill, and thanks, Aaron and Nancy. I always appreciate these opportunities. So Gord Cook, partner in construction instruction out of Denver. I always encourage folks to get down to our learning center there, where we actually have done some cool co-sessions with EVA on Next Gen Energy Star and how to get to zero energy very cost effectively. This particular one, though, carbon, I'm really excited about because it's only been in the last few years, right, that we've sort of talked about carbon and taken all the information we've had from an energy perspective and turned into a carbon focus. And I find it fascinating because, I bought my first blower back in 1987, I think it was, 88 probably. Been air tightness testing houses since then, and now recognize that, boy, we should have been talking about the carbon invested and the great job that builders who make houses airtight, the great change that they've made. So kind of interesting. So thanks for the opportunity, Bill.
Thanks. Yeah, and Gord, I'm glad you mentioned you'd love to be part of EVA stuff. EVA initiatives will be at EVA Summit again this year, and really looking forward to that. I think this is a great organization that pulls a lot of really good people together. So quick 2 seconds on myself. I work in strategic marketing for AeroSeal, the company. And I started out just focused on Aero Barrier, the building envelope air sealing technology. Now I also spend a little bit of my time on duct sealing as well, our AeroSeal product. But I've got over between 25 and 30 years in the building industry in a couple different ways. I started my life as an architect and way back then, about the time that Gord was buying his blower door, I was a couple years before that, I started my career as an architect. And we didn't call it sustainable or green. We called it energy conscious design. My master's in architecture from Arizona State, with some really well-known professors at that time anyway, was in energy conscious design and bioclimatic design were the terms we used. But it's been a passion of mine since I was actually in high school, getting buildings and houses to be better for people and better for the environment. So super excited about this. And as Gord mentioned, carbon is going to be nothing but a growing topic. So let's start by just thinking about what the carbon impact is of housing. And I wanted to throw this picture up there because it's a newer housing development, right? And there's a lot of houses in this picture. We build, just in the United States, about 1 million over the last 3 years, about 1 million single family homes a year. And every one of those single family homes has products in it that have carbon already embedded inside of them. And every one of those single family homes has to be heated and cooled. And that's putting operational carbon out into the atmosphere. So housing has a huge impact on carbon. So ergo, why we wanted to do this study and this analysis and then do this presentation. 40% of all carbon emissions are from buildings in the United States, and 70% of the energy use for homes is for heating and cooling. So we're talking big numbers where we can have a big impact if we can manage something and get better air tightness and less air leakage. We also have kind of these, as Gord mentioned, carbon is really only because it's been talked about a lot more over the last few years. And now we can really say it's kind of part of a new imperative, right? In that our government, the United States government, has said, hey, we want to be net carbon zero by 2050. And that's really quite a big deal. As you can see by this chart, is we need to, we're looking at where we're at now versus where we need to get to. Already mentioned that housing has a big impact on this. So we're going to play quite a big role in terms of where helping our country and helping even Canada and other countries around the world get to a net zero carbon status.
And I think that's important. I think that's important, Bill, to recognize it's not just the US, it's Canada. Every major corporation, if you watch, ads and so on, every major corporation is committed as well. So we're all in this, working at this together. And, it's an interesting focus, but we can get there.
Absolutely. And as we talk about carbon, we need to remember that there's really kind of, let's say, two components to it. One is embodied carbon. The other one is operational carbon. And operational carbon, as I talk about that in a second, is something that's very intuitive, very easy to understand. But embodied carbon, in terms of the construction of, say, for example, here, a single family home, is the carbon that's already embedded or included in all the different materials and products and technologies and so forth that are used in that finished house, that are finally in that finished house, whether that's a material you don't see that's inside the wall or inside of a roof assembly, or the concrete slab that's covered up with finished flooring, or whether it's actually the energy that's used to actually construct and build the house and install all those products. That's what we're going to refer to. That's what we mean by embodied carbon. And then operational carbon is really what energy is consumed by that house over the life of the house. And again, the majority of that, the biggest single percentage of operational carbon comes from the energy that is used to heat and cool homes. So you can imagine already how much impact getting a tighter air-sealed building envelope can make up, can enable us to get a lot lower operational carbon emissions. And then we put this slide together. You can see a slider, kind of a left-right arrow, blue arrow at the top of this slide. And on the far left of that arrow is things that are going to provide energy reduction. They help us reduce energy use, but they're going to do that a little bit less. And on the right side of that arrow are things that we can do to reduce energy in a single family home, but they're going to have a little more impact, or even a lot more impact, on reducing that energy use. So these are options for reducing operational carbon. On the left, we got high efficiency appliances like Energy Star appliances. We've got high efficiency HVAC equipment. On the right, we've got things like attic insulation, wall insulation, basement insulation. And when you think about those might even, they're going to reduce energy more, but they're also going to have more embodied carbon, right? Because they cover more of a surface area. There's more material included in the house. Then windows and doors, you've got glass and the vinyl window frames. And in the upper right, we put air sealing here because, and we'll get to this in a couple of minutes or in just the next minute or so, but it can really have a big impact on reducing the energy use used to heat or cool a house and have a minimal carbon impact. This next slide then says, okay, let's look at some of those things that we saw that had more of an impact in terms of they are able to reduce energy use in a single family home more. But what does that mean from an embodied carbon impact standpoint? On the left, in the big dash kind of outline, on the left are attic insulation, wall insulation, basement insulation, windows and doors. Again, they're going to do a nice job of reducing energy use, heating and cooling energy use in a single family home, but they're actually including more embodied carbon simply because it could be that they have higher carbon contents, things like styrofoam insulation, or even loose fill insulation, or the sheathing that you're using to create help to create an air barrier, bat insulation. But what are you doing? When you think about it, you're covering an entire surface area of the wall. You're covering an entire surface area of the envelope. And then windows and doors, if you're using double glazed or triple glazed glass or windows, you've got a lot of glass in there, which can be very high in carbon embodied carbon content, as well as the vinyl frames of the windows themselves. Versus, let's contrast that with air sealing. No matter how you're doing air sealing, if you're sealing cracks, gaps, and holes, there's just going to be less material, right? Less air sealing product material that's used in a home. So it gives you a lot of energy use reduction because of the air sealing properties with a minimal embodied carbon impact. And that leads us to kind of say an expression we've come to really like, which building envelope air sealing is the most carbon bang for the buck that you can get in the construction of a single family home. Why is that? Because you get the biggest impact on operational carbon, air leakage, dropping energy use more than a lot of other things you can do. It's got the lowest cost because you're going to use less material. And it's also, again, because of less material, it's going to give you the lowest embodied carbon impact. And then just to finish up on this section, carbon assessment tools that are available from an embodied carbon standpoint. The BEAM tool is an excellent tool that's been around now for just a few years or 3 years, and it's getting used more and more. And it includes inputs from product manufacturers. There's the EC3 tool also from an operational carbon standpoint. There's a variety of energy modeling softwares can help you do that, as well as knowing your fuel source emission factors from a utility company that's localized to where you're building that single family house or that single family house community. Ecotrope and RemRate are examples of some of those tools. And with that, I'm going to turn it over to Gord, and Gord's going to talk to us about kind of the impact that envelope air leakage has on carbon.
Thanks very much, Bill. So I'll just have you flip slides there. So if you could go to the next slide. And no surprise, I think folks have an appreciation for this. Typically, you're not on these calls unless you've had at least some building science understanding, but air leakage is that huge contributor to carbon emissions from housing, because uncontrolled air leakage accounts for as much as 40% of energy use, heating and cooling energy use. And so air sealing that building envelope reduces the energy use and therefore reduces carbon emissions. Let me just go back to that. When we talk about operational carbon, we're talking about the greenhouse gas emissions associated with the operation of your house, and the operation of the house, meaning the energy use of the house. So it's a direct relationship between energy use and operational carbon. That's why the RemRate, Ecotrope, Energy Gauge, those software programs that simulate energy use by default are therefore also simulating operational carbon. There's a few conversions that have to be made from millions of BTUs into tons of carbon, or kilowatt hours into tons of carbon, based on which fuel you're using. But energy equals carbon. And knowing that air tightness, we've known this for 40 years, air leakage, unwanted leakage of air, is the single largest component of heating bills and a huge factor in cooling bills as well. So big contributor to that operational carbon emissions. Next slide. Oh, there we go. No, go back one, sorry. There we are. Oh, there.
That's the next slide.
That is the next slide? Fair enough.
Yes.
All right. And so lots of studies have been done on this over the years, and it does change depending on the type of house you're building, 2-story, single-story, ducts and unconditioned space. It does change, but in fact, the evidence would say that the leakage, where that leakage is coming from, ceilings, floors, walls, plumbing penetrations, ductwork you're seeing, all of those are locations. It's actually hard to verify. We sometimes hear builders say to us, can we find the exact location of air leakage in our area or in our house? And it does take a little bit of investigative work. We can section off houses. We can do some infrared. We can do some smoke penciling and so on. But in general, over time, and lots of studies have been done by lots of different folks as to where that air leakage is. The real key is you don't know where it is unless you test for it. The nice part about the AeroSeal envelope process, you're testing for it while you're fixing it, which is always pretty interesting. So we'll go to the next slide. Here it is in graphic form. This is an old picture. Lots, if you just Google air leakage locations, you'll see this picture and many others where people, for consumers' perspective, have been trying to indicate where the air leakage is. One of the things we do need to understand, the forces that move air in and out of holes. Often we see this leakage going out through the top. This is indicative of winter heating bills, warm air rising, right? Stack effect. So holes at the top of the house tend to leak air out. Holes at the bottom of the house tend to leak air in during the winter time because of stack effect. Sometimes that air is being driven by wind, sometimes by mechanical effects, exhaust fans running or chimneys, but lots and lots of locations is where we need to understand air leakages from. Some are easy to seal, some aren't. That's always been the challenge, the difficulty. How do I get at these, especially in existing houses? In new housing, you would say at least I have a chance, but even still, it's tough to visually inspect an air barrier to say, yeah, that looks tight or not. We'll go to the next slide. And it really comes down to this. We've known about air tightness for a long time. It started to become a code requirement effectively in the US in 2009, in various state codes well beyond that or well before that. But the International Energy Conservation Code started to set out limits, or at least mention limits of air tightness, even though you didn't necessarily have to test the house. You were encouraged to air seal houses. And when we think about a house built in 2009, if you took all of the holes and put them into one spot, you'd have that hole of roughly 15 by 15, basically an open pane of window, if you will, maybe a little bit bigger than that, a small window open all the time. As the 2015 code was written, it suggested air tightness levels of 5 air changes in southern climates, 3 air changes in northern climates, and that's a 13 by 13 hole. The 2018 code is more specifically suggesting 3 air change per hour, 50 pascals. We won't go into the intricacies of air tightness testing at this point, all to say that we're just trying to reduce the size of holes in houses. What I always like to ask consumers is exactly how many holes would you like me to leave in the walls or attics of your house? Of course, their answer is none. We have lots of builders still, contractors who think, well, a few holes wouldn't be a bad idea. But let's be really clear. Homeowners expect 0 holes in the walls or attics of the house. So a 10 by 10 hole doesn't sound too good to a homeowner. Why would we leave that open? Go to the next slide, Bill. And as I said, it's been a specific requirement since 2009. And it actually got into the code not because of its implications on energy or on carbon for that matter. It was really to limit the potential for condensation in insulated attics and wall cavities. Imagine this: warm, moist air from your house that you cooked in, lived in, showered in, warm, moist air rising in your home, leaving through the lights, the plumbing penetrations, chimney penetrations, and so on, and getting into an attic that's gotten colder and colder over the years. Why? Because we've been adding insulation to attics over the years, from R12 in the early 70s to 20 to 24 to 28 to 30, now to 49, in some cases 59, depending on what climate zone. The more insulation you put in the attic, the colder that attic is. And if any warm, moist air is leaking into the attic, it's going to condense on the underside of the roof sheathing. So let's be really clear. Air sealing is a building science issue. No warm, moist air into cold cavities. At the same time, obviously, huge benefits from an energy perspective. So keeping that in mind, it's been a requirement since 2009. Next slide. Seems like a little delay. All right. So the key to this is the additional benefits of air sealing. We're going to be talking carbon to show you some results there, but it's really to help prevent moisture fermenting wall and attic systems. uh, clearly experiencing dramatic savings on home heating, cooling, enjoying a more comfortable home, less drafts, less noise, less dust, less bugs. And interesting enough, in the southern climates, less humid air coming into the house. We know we have humidity control problems in the southeast, the central Texas, and so on. That to some extent, that's warm, moist air leaking into our houses from outside that now we need our air conditioner to remove latent removal. So lots of advantages. I'm highlighting recently the wood smoke that we've experienced in the West primarily. Boy, if you're living in those kinds of areas, you would say, first thing I want is a really nice tight house with controlled ventilation, so I don't bring in unwanted amounts of or excessive amounts of unwanted air that would bring in wood smoke. So lots and lots of advantages to air tightness, and why consumers would say zero holes in my house, please. Next slide. And we do know that there, and I'll hand this over to you, Bill, we've tried for years to find air sealing methods, understanding that our houses, for the most part, are made out of air barriers, right? Drywall and foams and sheet goods like WRBs like Tyvek, even sheet goods like OSB. Those are all materials that could be defined as air barriers. The trick is, how do I seal the joints, the intersections between those? And that's really been the crux of this, is how do I create a continuous air barrier, recognizing that we already have air barriers in houses? How do I create an air seal around those? And Bill, I think you have some thoughts on that.
Yeah, so there's really, when we think about it, there's the ways that we've actually done this over since we've been building single family houses and then been thinking about sealing air leaks, right? Could be lumped into two basic categories: manual and something that's not manual. So manual air sealing is, there's wraps that are used inside, there are house wraps that are used outside. There's a tuba caulk where somebody's, people are walking around sealing around envelopes or sealing cracks, gaps, and holes that they can see. On the upper right, you can see where you've got electrical wiring going in through studs, or using foam on the lower left to seal around a window. Somebody with a tube of caulk in the middle bottom, or even at the around right above the basement where the first floor is hitting the foundation, where we're going to spray foam, right, to prevent cold air from getting in there. Those are all manual methods that have worked at some level of success throughout history. There's also really an automated method too. And without going into this in detail, that is aero barrier from aerosol envelope. But it's an automated method that's immediately verified because we're using a continuous blower door test. So when we think about that air sealing, there are essentially two ways to do it: one manual, one automated. I'm sure in the future there may be other automated methods that are introduced into the market as well. But right now, that automated method is aero barrier. And next, what I'll do is I'm going to cover a little bit of information on embodied carbon. And remember, embodied carbon, again, is that carbon that's represented in the products that we're using in the house. Anything from just materials like concrete or sheeting or insulation to the finishes that we see, whether they be countertops, finished flooring, finished wall, so on and so forth. So one of the ways, or the way, that we understand how much embodied carbon is in a house is hopefully we would have what's called an EPD, or an environmental product declaration, for every single product that's used in the construction of a house we're building. In this case, in our presentation today, we're looking at single family houses. However, if those of you who are on the webinar have tried to research this or tried to find some, you found what we've found as well, which there really aren't a lot of building product manufacturers that have developed or had EPDs produced for their products. And the ones that have typically are the building products that have higher levels of embodied carbon. We'll cover that on the next slide, but they're going to include things like brick or concrete or things like that. I can talk to you as working at a building product manufacturer, the reason that part of the reason, the number of reasons why these haven't been done yet. One, they take time and people resources, as well as money to get done. They're not inexpensive actually to have done. They're higher cost than you would think. And then two, it just takes a chunk of time, and it takes a chunk of time from somebody who's working at the company to be able to manage that process. There are great vendors out there, third-party companies who do the work. I'm happy to report that we at AeroSeal and AeroBarrier have been really engaged in the carbon conversation for a while now, and our EPD is actually in process and should be done by early fall. And we used an excellent, the firm we hired to do that for us, we're extremely happy with, and we're real excited to get that done. But typically you'd look for EPDs and they're going to tell you exactly how much embodied carbon is in that product. And those are done by a neutral third party who follows a very specific process and meets very specific standards so that you know that that data is correct. In terms of, again, we mentioned there, when you think of all the different materials and products that go into a house, some are going to include a lot more carbon and some are embodied carbon and some will include less. Things like exterior wall cladding or finishes, whether that be brick or clay, or even, plywood sheathing, any type of sheathing, whether it be zip wall, those are all materials. Again, not only can they be high in carbon content, but you're covering the entire surface area of the envelope. So there's just going to be a lot more of that material that's used. Foundation walls that are made of concrete, footings and slabs are made of concrete, which is very high in embodied carbon. There's been great efforts, and still are today, where there's already some concrete materials that are in the market that are much lower in carbon. So we're seeing some good success making progress there. Windows, as I mentioned earlier, can be high in carbon. Some of the materials used in floors and roofs and garages. Now, where do we get a look?
So Bill,
Yeah,
just
sorry,
go back
ahead.
that one slide, sorry.
Yeah.
So just to give folks a sense, this was a 2,500 square foot house, I think it was 2-story house, brick cladding, obviously, and just showing the top 9 contributors. Notice that insulation doesn't even make it on there, right? Even insulation isn't there. This isn't all of the carbon emitted during manufacturing of the house, but it shows you the top 10. And notice even the difference if you look at, say, the foundation, concrete elements and the brick elements, just the huge percentage, and then the quick drop off to all the others. So this is the exercise that is done through the beam tool, for example, one example of how a particular house is done. I would just encourage builders, others on this call, if you haven't seen one of these, go ahead and have it done. We do it for builders to give you a sense of where the big contributors are in your particular house, just getting a sense of the most important elements.
Yep. And then where can you find EPDs? They're essentially either you can find them on manufacturers' websites, or you can go to basically what they're called program operators, and they essentially will they'll certify and house the EPDs for a variety of building products and building materials. And those in the US, those could be the UL Spot database. ASTM International has their online database, as well as the NSF, the National Science Foundation. And I believe Aaron actually put a link to a good website that includes you can go find a lot of EPDs there as well. So look for that in the chat.
Bill, we've curated all EPDs known to us at the eba.agromedes.com website. So they are all findable there as well.
Very cool. And very soon the aero barrier EPD will go up.
Amen.
All right. Now a little bit, let's think about, so because we don't have a lot of data on the embodied carbon of a lot of specific products, it doesn't mean we can't actually still have a positive impact on embodied carbon. So until we get a lot more manufacturers to provide us with EPDs, we as professional, as single family home design and construction professionals, we can actually think about, okay, where am I going to use more product and where am I going to use less product? So as we think about the things that are used for just air sealing products alone, again, we're using that sliding scale at the top. More material is represented on the left of that blue arrow at the top of the slide. Less material is represented on the far right hand side of that left right arrow, blue arrow at the top of the slide. So things like membrane, sheathing, and fluid applied air sealing materials do a great job at air sealing, right? But they include a lot more embodied carbon. It could be because of the actual chemical makeup of their product. It could also just be because you're using a lot of that material to cover the entire surface area of either parts of the envelope or the entire building envelope. In the middle, we'd kind of put tapes and gaskets and think of why. Because again, what if let's say you're sealing the joints of sheathing, 4x8 pieces of sheathing, whatever brand that is you're using. That tape there's going to be a lot less tape used than there is of the sheathing, right? And it's integral to actually making sure that the sheathing becomes a continuous air barrier. or you've also got gaskets around conduit and pipe penetrations and things like that. Next would be caulking and foam, where somebody's going to go along and say caulk or use foam along a continuous linear joint between two materials. It could be at a sill plate. It could be in between pieces of all the drywall joints, right? So there's less material there. Finally, the least amount of material is going to be, again, our friend aero barrier. And the reason is it's leak specific applied. The sealant only adheres and sticks where there actually leaks. So if you look at, for example, a sill plate, aero barrier is only going to self-install or adhere where there are leaks along that sill plate. So if you've got a 50-foot long wall, it's not going to be 50 feet of linear aero barrier. It might actually only represent 15 or 20 feet of actual material because it's only sticking where there are leaks, where the sill plate's not sitting firmly on the concrete slab or the top of the foundation wall.
And Bill, I'll just comment that years ago when they were doing weatherization programs, that is low income housing, trying to make them more comfortable, they used to have contractors go in, caulk, tape, sealants around electrical outlets, plumbing penetrations, and so on, and then would test after and realize, geez, we didn't really make much of a difference. So then they started using a term called blower door directed air sealing efforts.
Yeah.
Okay, so give the contractor with the sealant a blower door and say only use the caulking or the sealant where you feel a leak when the blower door is on. And I love when I first saw Aero Seal, I'm like, okay, this is blower door directed air sealing. I see lots of beads of caulking, lots of beads of foam. That red foam, I love that product down at the bottom, but I see it applied in exactly the wrong places. I see it along the baseboard or between the subfloor and the wall. I'm like, that's not the right place. One, that should be caulking, not a foam product there. So using the right product in the right location, but then only applying the caulk or sealant where you need it, I think is so fascinating from a Aero Seal's perspective. So keep that term in mind, those are on the call. Blower door directed air sealing is very cost effective.
Next, we're going to cover operational carbon, and Gord's going to talk about a few slides here.
Yeah. So let me walk through a little sense of what this was about, and I'll just remind you that your energy rater is in fact already giving you your total annual energy use. Bill, I think we need to flip next slide, please. Thank you. And so the operational carbon, as Bill mentioned, is a function of energy use, the actual annual energy consumption, simulated energy consumption, what fuel you chose to do that with, and then the emissions in generating that fuel or that energy choice. So as an example, I'm suggesting that in many markets in the US, your heating and domestic hot water are done with natural gas. So we'd want to know the operational carbon emissions associated with the burning of natural gas. And then the appliances, lights and appliances and cooling are done with a fuel known as electricity. We'd want to know what the emission factors were associated with the generation of that electricity. We'll go to the next slide. And take that one out. Yep, sorry. Or go ahead. Next one.
No, you're good. You're good.
No, it says air leakage impacts. Yep. Oh, sorry. Yes. Go back one then. Sorry. My apologies. And so thinking about when we do the calculations, when I show you the calculations, you'll see what that looks like as to how do I apply emission factors to natural gas and how I apply emission factors to electricity. So you can flip that next slide. Just go right past that one. Thank you. And this was an important study, an interesting study that you folks did, Bill. You partnered with Ecotrope to get a sense of where those levels were. Perhaps just comment a little bit on that.
Yeah, so what we did was we actually worked with Ecotrope, and if you're not familiar with Ecotrope, they're a company who a lot of information and data from HERS rating from single family homes is fed into the Ecotrope database, and you can do a lot of interesting analysis and studies because of just the vast amount of really good information they have. And what we wanted to do is we wanted to say, let's, since air sealing is important, we know it's important. We know you'll see in our analysis, we're going to show that it makes a really good impact on operational carbon reduction. Let's look, before we get into that analysis that we did, let's look and see where are we actually at today in 10 cities in the United States. And they will sync up with the same 10 cities we did our carbon reduction analysis in terms of what are home builders building, like where are we at in terms of ACH 50 or air leakage levels. So we looked at these 10 cities. You can go from across the top or bottom: Houston, Phoenix, San Diego, Atlanta, Raleigh, North Carolina, Indianapolis, Seattle, Salt Lake City, Chicago, and Minneapolis. And what you see on this chart, they're little pictures, right? But if you look at them in aggregate, it's a really interesting view. We were looking at each one of these individually, and then we decided, hey, let's throw them on one slide, and it actually tells a really cool story. So first, let's note that this is for a 12-month period from September 10th, 2022 through September 9th, 2023. And these were single-family homes built in each one of these markets. What air leakage level did they achieve? The vertical red dashed line that's really thick, that represents where 3 ACH 50 is, which is the most common code, right? Where in markets that have a code, that's what they're trying to hit. So you look at Houston, there's a lot of houses being built above 3. Whereas you look in Minneapolis at the lower right, the vast majority of houses are being built below 3 air changes per hour. Kind of makes sense, right? Really far northern climate. Having lived in Minneapolis for 30 years, I can tell you it is by far the coldest large city in the United States of America. I experienced that firsthand. But even look at San Diego. San Diego's got pretty good distribution. A lot of houses built before 3 air changes per hour. So you'll be able to get these slides, I believe, afterwards. We're going to submit those as a PDF to EBA. This webinar is also being recorded if you want to come back and look at parts of it. But we found this to be really kind of fun and interesting to look at, to see where we are at from, those graphs go from 0 ACH 50 on the left, on the scale, all the way up to like 6 or 7, maybe 7 ACH 50 or higher on the far right. And just to look by city, how are they doing? How are builders doing? Where are they building? From a 3 or 4 or 5 or 6 or 7 or 1 or 2 air changes per hour at 50 pascals of pressure.
And Bill, I do think it's fascinating just to imagine. It's been a code requirement since 2009, International Energy Conservation Code, that all houses be air sealed. And look at the variation. This is really pretty interesting to think about the variation and how, boy, clearly the way the code's being interpreted, adopted, and implemented varies by city to city, and this is tens of thousands of houses, so we can't just say, oh, it's a one-off. And so on. This is pretty interesting data to show that spread, if you will. And then, as you say, let's go to the next one. I just want to give a quick example of that variation. Yep. Here is Minneapolis. Notice that everybody's pretty much under 3 air changes, have been for years. Why is that? Cold climate, you might say. Moisture problems, sure. Is there a particular focus on energy? One of the things I like to point out, hopefully this isn't seen as controversial, but Minnesota's had statewide requirements for continuing education for about 30 years. EBA's located in Minnesota, has done lots of education. Aaron and Nancy, you will know, this tends to be a better educated group of contractors who've kind of understood that there's almost 5,000 houses. You can see there are 4,700 houses. This is pretty interesting. And it's because they had moisture issues in walls and attics, and because of that consistent training. If you go to the next slide, and if we drove about 4 hours to Chicago, very cold climate. Wow, should this be where they're at? I mean, this is showing you that there are a good number of builders, not quite, well, just a little more than half, I guess, of the houses done. Here, only 2,400 houses, half the number, but it's still a huge number of houses that we would say as building scientists put you at tremendous risk. Forget carbon, put you at risk as a builder from a moisture, condensation, drafts, comfort, all of those things, not to mention oversizing of heating and cooling systems as a result of these higher than needed, higher than expected air tightness levels. Pretty fascinating data. I really applaud AeroSeal for working with Ecotrope to show that data.
You bet. Yeah, and Gord, I think now you're gonna take us through the analysis that we did, which
Yeah.
is a really cool analysis modeling the impact of carbon.
Yes, thank you. And it is a modeling exercise. You can go ahead and flip the slide there. It was a modeling exercise. We chose a typical single family house in 10 different cities representing climate zones 2 through 6. To give you a sense, we modeled 6 different levels of air tightness from 7 all the way down to 0.6 past those levels. And we captured the total energy consumption. And that's important to understand when you see these numbers, total annual energy consumption, which includes heating, cooling, lights, appliances, domestic hot water. The total number is what we thought we would do. And then we converted the energy use to the operational carbon using the gas and electric, using national average grid emission factors, and therefore the tons of equivalent CO2 associated, say, with a kilowatt hour. Now, we do need to understand that there are different grids, different markets. We use the national average grid emission factors. I would encourage you to do an operational carbon in your own houses. We can help you with that. AeroSeal can help you with that, knowing your individual grid. But in this one, it's the national grid. And we captured space heating, cooling loads as well at design conditions. So that gives you a sense of the analysis. Go ahead. Locked up.
Yeah, it switched on my end.
There we are. There we are. So, and then the house we modeled, 2-story house, there it is there, approximately 2,350 square feet, slab on grade, heated with natural gas, insulated to ICC 2009 levels for climate zone 4. The same insulation levels were used in every city. And you go, oh, that's a little unrealistic. Well, we are trying to highlight the impact of air tightness. So keep that in mind. And again, I mentioned space, heating, cooling consumption, domestic hot water, lights and appliances, that total annual energy consumption. Go ahead, Bill. And there's the cities, Houston through Phoenix, San Diego, Atlanta, Raleigh, and so on. And we used a natural gas emission factor, the tons of CO2 per therm of 0.0053 tons per therm, electricity 0.0007 tons per kilowatt hour. And again, I'll mention that your electrical grids may differ dramatically from this. This was a national average. The best in the country is typically New York State because they buy their power from the that goes over the falls in James Bay, Quebec. The worst tends to be in Hawaii because they import a lot of their diesel and bunker oil to generate electricity. So it will vary by location, but we've used national averages. Go ahead. And here you'll start to see the differences, if you will, and you'll see the air change of power and effect on just in graphical form on operational carbon emissions. The darker green to the left of each bar is at 7 air changes. The lighter green is at 0.6. And you'll notice in each case, in every city, even San Diego, although their operational carbon is much lower because they basically have no winter, no summer. Minnesota is very high because of that ultra cold winter. But you'll notice in each case, in each climate zone, a pretty significant or at least noticeable change in operational carbon emissions. If we go more specifically, that sort of graphical form, just keep that in mind. That's a big bang for buck. But if we went to that next slide, there, we'll just give that a second. Here's showing operational carbon reductions for Minneapolis. I just thought I'd show the most dramatic case from 7 air changes down to 0.6 on the left-hand side to tons of carbon reduced on the right-hand side from 12.77 tons down to 10.82 tons. In other words, a 15% improvement. Remember, this is an improvement in total carbon emissions, lights, appliances, everything. If we just did it on the heating load, it would be dramatically higher as a percentage, and even a nice improvement from 9% improvement from 5 down to 1.5. Also notice from a heating load design, second column in, from 59,000 BTUs to 42,000 BTUs. In other words, a smaller furnace. Typically, it's going to be a 75,000 BTU furnace if you're 7 air changes. It's going to be a 50,000 BTU furnace if you're going to be at 0.6 air changes. So we're seeing a really nice reduction in size of heating equipment that would go into the house. Cooling fairly modest in terms of in terms of thousands of BTUs, from 16,000 BTUs to 13,000 BTUs, from say a 1.5 ton air conditioner down to a 1 ton air conditioner. Again, just by this one simple change of air tightness, understanding with one phone call to one contractor, if you will, I can get to these better levels of air tightness. So pretty dramatic. So that's Minneapolis. We'll probably want to look at another city just to give you a sense. There's the Chicago, again, knowing that you're going to say, well, in Minnesota, they're already at that 1.5. Well, we saw in Chicago that, boy, maybe a bigger opportunity just by number of houses that aren't able to meet those requirements. But again, a very consistent 13%, 12 to 15% reduction, in this case 13, 7 to 9% reduction from going from 5 down to 1.5 every city. And again, you're going to be given access to all of those cities. You can have your own energy rater do modeling for your market to say what would be impact in my market, but pretty powerful to see where this is headed. Keep going. And I'm not going to do all the cities, at least I hope I'm not, but even in Atlanta, showing that. So we'll go, there's San Diego, the lowest of those, if you will. So even in San Diego, almost a 4% improvement in San Diego. In fact, one of the few things you can do in San Diego to see any significant drop in operational carbon, because they've started off so low, but a 4% drop from getting 7 down to 0.6. And we know in San Diego, houses tend to be a little looser. Why? Because they've had no winter and no summer. So we're seeing an opportunity here in every climate zone. Go ahead, Bill. And just showing the summary of all of that on the right-hand side. I won't go into each number, but significant carbon emission reductions in every city from 4% to 15%. Greater percentage reductions in colder climate, no two ways about it, but also helpful reductions in heating capacity requirements in colder climates. Not a big change in tonnage in terms of air conditioning, but I will say big change in reduction of latent load requirements, that is air leakage and the moisture that comes in associated with that. These reductions that you're seeing here are primarily in the latent load reductions. And I'll reminder, this is total overall operational carbon reductions. So a nice improvement in all of those houses and very dual numbers. Go to the next slide. And thinking about in hot climates, a bit of a summary of this, a reduction of 4 to 10 tons over the next 30 years of every house sealed. 4 to 10 tons, not tonnage in terms of air conditioning capacity, tonnage in terms of CO2 reductions. And that's the equivalent of carbon sequestered by about 150 to 400 mature trees, depending on the climate zone, or the carbon equivalent of 300 propane tanks, barbecue tanks. And in hot climates, reducing air leakage is one of the only improvements that can be made to the envelope that's cost effective. It's really difficult to justify on carbon alone the addition of more insulation. In cold climates, wow, even more dramatic, right? 15 to 30 tons over the next years. That's the equivalent of 600 to 1,000 mature trees sequestering carbon, 1,000 propane tanks. And in this case, cold climate, we've always known, has been the most cost-effective strategy for improving the building envelope, both from a building durability, less condensation in cavities, plus lower heating and cooling costs. So very powerful that we see these summaries that are able to, these impacts that we're able to have. Go to the next slide. And I just thought I'd compare that quickly to the impact of other energy efficiency measures. So let's do a couple of quick examples here. You had mentioned earlier, Bill, that windows were a nice method of improving energy performance of houses. We often wonder, what about that third pane of glass, the embodied carbon associated with that? Notice that windows this is in Chicago. Notice in Chicago, we get a 0.27 ton reduction in operational carbon, but we had to expend an extra 0.5 tons in embodied carbon. So it's still a really good number. It's about a 2-year return on carbon invested. So that's really good. But still, it would say it's slightly more embodied carbon. I'm not saying don't do triple glazed windows. Of course, you should do triple glazed windows in Chicago for any number of reasons: comfort, condensation control, and now we see embodied carbon. So that's pretty useful. Lots of other advantages to triples. If we go to the next one, you're going to see insulated sheathing. A big fan of insulated sheathing. Again, in Chicago, I'm imagining folks on the call are cold climate. And you might say, is this worthwhile in other climate zones? Go ahead and run it in different climate zones. But here again, we're seeing a 0.41 ton per year reduction in carbon, 0.27 for windows, 0.41 for insulated sheathing, going from no insulated sheathing to R10, 2 inches, but an uptake of embodied carbon, 2.4 tons, but still a really nice return. In Chicago, within 6 years, before 2030, you're going to have reduced your carbon emissions out of that house, even though you invested in insulated sheathing. So another good return on carbon invested. But if we contrast that, say, in that same house, go to the next slide, with operational carbon, notice that it's 0.31 tons, not as much as the 2-inch of insulated sheathing, more than the triple glazed windows, but with basically no embodied carbon. The extra bit of sealant that's put in that house, and you're gonna prove that to the world come August, if you will, Bill, with the embodied carbon of. But we already know that the embodied carbon is going to be so small, is almost imperceptible. So an immediate return on carbon invested. So you see, there's 3 really good measures to take. Which one would you do first? Well, of course, I'm going to suggest that you always want to do air tightness. Why? Because it's been a code requirement since 2009. It's all over the map. You need it for noise, dust, bugs, moisture control, air quality control, so on. And now you're seeing a really good bang for buck. And so as you get planning and thinking about how am I going to do insulated sheathing, let's at least get to air tightness in the short term. So we'll go to the next slide just as we think about finishing up here. And so by all means, let's summarize, Bill, for the group on the call, these key learnings. I'm going to say for over 30 years, in fact, over 40 years, we've known the value of reducing unwanted air leakage, primarily to avoid condensation in insulated cavities, but also to control humidity, specifically in hot, humid climates, but to improve comfort. And Bill, you'll want to follow up and just give it from an energy/carbon perspective what the impact is.
Yeah, in terms of, if you look at the percentages we saw, as Gordon mentioned, in the modeling we did include overall energy use, not just energy use for heating and cooling. So the percentages we saw, which were still very good in terms of reducing operational carbon, would be even greater if we just compared that to heating and cooling energy reduction. And Gordon, maybe that's a follow-up for us, is to maybe look at those numbers, for just heating and cooling energy use, because they're going to jump quite a bit. But we, just getting back to a slide we had earlier in the deck, I think it's really good for us as an industry and as professionals to think of air sealing as being the greatest carbon impact bang for the buck, meaning what are you spending on cost to do something? What are you spending in terms of embodied carbon represented in what it is you're doing to reduce energy use? And air sealing really scores very high in both of those. It's going to give you the greatest energy reduction in terms of, if we think about that DOE study that showed up to 40% on a single family house, up to 40% of the energy used in that home just for heating and cooling. If we can reduce that 40% with air sealing, that's going to be a greatest single impact on energy reduction. Then it's going to be a very large impact on carbon reduction with very little, not a lot of cost spent, as well as not a lot of embodied carbon put into the home. So the greatest carbon impact for the buck would be air sealing. And to me, I mean, that's a great place to kind of maybe finish up our webinar. Gord, you may have a final comment as well before we look at any questions.
I'll maybe do it by decade. That is, the early research on this was done in the 70s and the 80s on air tightness. And the first and foremost thing that they wanted to do where they were trying to make houses more efficient, and they tried to put in insulation into cavities and then realized, oops, that's causing moisture problems. So in the 70s and 80s, they found the single best way to avoid condensation problems in buildings was to make them airtight. That continues to be the case. In the 90s and the 2000s, there was a switch of more of a focus to healthy indoor environments, and they found that the single most cost-effective thing to do to improve the air quality in a house was to make the building airtight to avoid unwanted contaminants like pollens, dust, wood smokes, and to properly ventilate. And now in 2000s to 2020, the focus, or 2000s to 2010, the focus was again back on energy and energy reduction. And again, air sealing still continues to be the most cost-effective way to reduce energy consumption. And here we are in the 2020s, and the focus is now switched to carbon. And it turns out air sealing is the most cost-effective way to do carbon reductions, at least operational carbon reductions. So here through the decades, air sealing has been a code requirement since 2000. It's been researched since the 1980s. Boy, it's time to kind of solve this. And I'm really pleased that we now have an automatic way of doing air sealing. It just takes all the guesswork right out of air sealing and relying, I would say, on a technology. And we've always looked, right, for technologies in houses that gets somehow helps out with the problem we have with skilled trades training. And here's one you could take off your plate and say, you can just get this done. So I appreciate what AeroBarrier and AeroSeal brings to the table. Thank you for that. And that probably is a good time for questions.
Yep.
Great. One question I had was, have you thought about the health impact as well? Because one of the things that, in the pictures that you showed, when we may have adhesives and sealants that we can't control that are adding volatile organic compounds to the home. And I think, Gord, you gave a great example of a problem that happened up in Ontario with some PL400 adhesive. So I understand that AeroSeal envelope is very benign in the environment and has some data backing that. But Bill, can you just talk a little bit about how you see this perhaps improving the health impact of the building as well?
For sure, yeah, both not just both during construction in terms of how quickly trades can get back into the house to resume their work, but also in terms of the finished house itself. So the sealant used, we call it the AeroBarrier X1 sealant, is actually Green Guard Gold certified, which is a very, very strict certification standard for safe materials. It's the same level of Green Guard Gold certified can be used in hospitals and elementary schools. So that's an indication of the level of safety we have to be able to provide to get that certification. I had done some quick analysis too for some of us internally just in the last month, where when we're ultra low VOCs, volatile organic compounds. People today, and this started probably 10, 15 years ago or a little more, people started saying, hey, when I go to repaint my house, I want to change the color of my living room, my bedroom, my dining room. Hey, there's now these paints available called low VOC, low volatile organic compounds. The government doesn't actually regulate that. There are a couple of industry organizations who do, and they do a really good job at it. And to be labeled a low VOC paint, you have to be basically at 50 parts I forget the measure. I don't want to take our Q&A slide off my screen, so I can't pull up the document I'm trying to refer from, but it's around 50, a level of 50. AeroBarrier is at about 9. So we're ultra low VOC. During the construction process, literally 30 minutes after we finish and pull our equipment out of the single family home, other trades can be back inside and begin working again.
Fantastic. Another question, and Gord, I love the term that you introduced to us about blower door directed air sealing. I think that's a really great way to think about this product. Is there anything that we, as we're installing this or having the AeroSeal envelope contractor install this for us, when we're doing blower door directed air sealing and we're over pressurizing the house and driving that product in, and let's say I want to target a 0.6 ACH 50, Is there anything I need to think about or any studies that have been done that say an overpressurization, I need to go for a certain ACH 50 because then when I test it with my standard blower door, any studies or results around that or things that we should be aware of as we look to install this product in our houses?
Yeah, we actually did a little paper on this for AeroBarrier at CI because the numbers are different. For a start, when you're doing AeroBarrier, you don't want the sealant going into bathroom fans or other mechanical devices. So you do tape off certain things that, depending on how good those dampers are. In fact, you tape off window sashes because you don't want the sealant getting in the operable section of the window. So when you take that off and do your final blower door test, the number is different. And it does vary depending on the region that you're doing it. I would say windows sold in the north are more airtight than windows sold in the south. So depending on your window supplier, our experience has been around a half an air change difference. Not well, the tighter the house, the less the number, but the less the variance. But say if you want to get to 0.6, we would say seal it to my opinion, down to 0.3. And now it loosens back up. If you want to get to 1.5, go to 1.
Mm-hmm.
And then it'll loosen back. Not loosen, as somebody, I shouldn't use the term loosen back up, the final blower door number. And it really is a function of how good are the backdraft dampers in your fans. I could put a plug in for Brown and Panasonic, for example, because they now have new series of fans. Not necessarily being bought, but you could specify them that have much tighter dampers to them, much better dampers. So, good HVAC partners recognize that their equipment has to be better as well. Choose windows that publish their air tightness data so that you have a better sense of where that's at. But there is we call it a variance, and it's definitely there. So I'll leave it at that, knowing the interest of time.
I think that's great advice. Bill, anything to add to that?
Yeah, we do. Our licensed installers who install AeroBarrier, they are trained to go below to the kind of deltas or difference that Gord mentioned. So if your builder customer wants to be at a 3, we're going to sail down to a 2.5. If you're into the same numbers Gord was mentioning, so that we can allow for things. We'll have to remove some of the little bit of the protective film that we use, as well as sometimes depending on the type of window or level of window that's being used in a home, it's going to reintroduce some air leakage as well. So we do account for that.
Great. Another question we had was, is there any studies or data that shows that AeroBarrier works to improve interior vapor barriers for heating in heating dominated climate zones more than in cooling dominated climate zones? And I think, Gord, this is kind of around our conversation we're having as we prep for today's webinar.
Yeah, really the key is we've always had this term vapor barriers, got into the codes in the 1940s because the insulation manufacturers knew that if warm, moist vapor got into wall cavities, insulated wall cavities, you'd have condensation issues. What we didn't realize at the time, it wasn't the vapor diffusion through the drywall or the plaster or the lath and so on. It was the air leakage around it. So it turns out 100 times more moisture gets into walls and attics via air leakage than by vapor diffusion. So by all means, continue to put up your vapor barriers or not. More importantly, make your house airtight. There's really good evidence. If your house, and we know the number, if your house is under 1.5 air changes, the chance that you'll have condensation within any cavity is dramatically reduced. That's why that number was set by the Super Good Sense program back in the day, by the R2000 program in Canada, by Passive House. Passive House 0.6. Why? Because Passive House advocates for much more insulation in walls than, say, standard code. And the more insulation, the tighter the building needs to be. So it's the air sealing benefit. Don't think of it as a vapor barrier because it itself is vapor permeable, but not enough water vapor goes through it. It's the air that's moving through the holes that aero barrier, aero seal is sealing that's most important to you. And that's always a distinction. Come back for more learning on that if need be. EBA sessions, building science sessions, we go into that pretty extensively. CI Live, aero barriers, all of those trainings would say, worry less about vapor barriers, worry more about air barriers. That's what controls the amount of moisture that gets into wall cavities or ceiling cavities.
Fantastic. Bill, final thoughts.
I think just we're love to be a part of EBA. Glad we could do this. I think this study for me was even individually was just real exciting to do, to show the actual impact of air sealing on operational carbon. I would love to follow up and say, hey, what are those percentages just for heating and cooling energy? I think that might be a good next step for us to come back to this to our broader community with. And then I'll give a plug also to Home Builders Can, right? The new effort that's being spearheaded by Rocky Mountain Institute. We're a supporter of it, and we're super excited to be part of that. But they're now going to be diligently working with home builders, specifically with some home builders, to kind of improve this. And to me, it's like, as we think about not just energy efficiency, but we say energy efficiency, the benefits of air sealing, energy efficiency, indoor air quality, more comfortable, right? Less insects, pests, and rodents inside the home. I think now we can add, less operational carbon. And when we talked on carbon impact at FIASCon actually last year, that's one of the things we ended on was, hey, this is a way to market and sell. There are some of your consumers you can also say, because we air sealed your house down to, say, 1.5 air changes per hour or 2 air changes per hour, or even 3 versus the average construction house at a 7, 8, or 9. You are saving this many trees. You are emitting this much less carbon. That's a marketing and sales impact that home builders can use. So I think maybe that's a good ending thought.
Absolutely. And Nancy just put it in the chat. Nancy, thank you so much. But
So
EBA also is one of the founding supporters of Home Builders Can. And we actually have a shoulder event with them on October 1st at the EBA Summit in Salt Lake City. And they will be doing a session around decarbonization for homes, and talking through some of the methodologies and learnings that we've had over the past really couple of years. So, and of course, Bill and Gord will look forward to seeing you at that event in Salt Lake City as well. So thank you so much for spending your time with us today. This will all be posted up at eba.org and also available on our Better Homes, Better Future podcast. Thank you, gentlemen.
Thanks so
Thank
much.
you, Aaron.